Methods of measuring or estimating soil moisture. To determine the required depth of irrigation water to be applied at any given time, the irrigator should first estimate or measure the amount of available moisture in the soil within the root zone depth. There are several methods for doing this. Soil sampling and drying. This method involves sampling each type of soil in the field at desired depths and at several locations. The soil samples are weighed, dried, and weighed again. The difference in weight is equal to the weight of the moisture. Usually this is expressed as the percentage of the weight of the dry soil. Tensiometer. The tensiometer consists essentially of a porous cup filled with water and connected by a continuous water column to a vacuum measuring device, either a gauge or a manometer. The cup is buried in the soil at the desired depth and measurements are read above ground on the vacuum indicator. This instrument measures soil moisture tension directly. A moisture characteristic curve for the particular soil being irrigated is required to convert moisture tension measurements to percentage of available moisture in the soil. Electrical instruments. Electrical instruments operate on the principle that a change in moisture content produces changes in some electrical property of the soil or of an instrument inserted in the soil. In most cases, this property is electroconductivity. Electrodes are permanently mounted in conductivity units. These units are usually blocks made of nylon, fiberglass, or gypsum. These blocks are buried at the desired depth, and changes in the moisture content of the soil are reflected by changes in the electrical resistance of the blocks. Resistance or conductance meters are used to measure the resistance. It is necessary to calibrate the blocks in the field by comparing the resistance readings with the soil moisture contents determined by oven drying samples taken from the same relative position as the blocks. Gas pressure instruments. Instruments such as the carbide moisture meter utilize the principle of chemical drying of the soil sample. A reagent such as calcium carbide is mixed with the moist soil sample within a sealed chamber. The chemical reaction of the reagent and the soil moisture produces acetylene gas. The gas pressure registers on a gauge that is calibrated to indicate the wet weight moisture percentage of the soil. Convenient tables are available to convert these values to dry weight moisture percentages. The reaction and readings normally require about 3 minutes per sample. Feel and appearance method. This method is widely used to estimate the amount of available moisture in the soil. Samples are taken from various depths and at several locations in the field. A soil sampling tube, auger, or post-hole digger is used. The feel and appearance of the samples are compared with a table or a guide, and the soil moisture level is thus estimated. With practice and experience, the irrigator should be able to estimate the moisture level within 10 to 15%. Evaporation pan method. This method uses the relationship of crop consumptive use to the evaporation from standard evaporation pans. Evaporation pan data are approximations of consumptive use and are not measurements of soil moisture. The amount of soil moisture used in a given period must be calculated. This calculation is made by applying a factor to the crop that is to be irrigated to the depth at which water evaporated from the pan during that period. This calculated amount then represents the soil moisture used by the crop. Moisture accounting method. Consumptive use values are used to maintain a daily inventory of the remaining soil moisture. Starting at a time when the moisture level in the soil is known, a bookkeeping system is set up whereby the computed consumptive use is subtracted daily from the recorded available moisture in the soil. Rainfall and irrigation amounts are added to the moisture balance when received. The success of this method depends on accurate measurements of the water holding capacity of the soil, determination of daily consumptive use rates, and measurements of rainfall and irrigation amounts. Irrigation water management. Introduction. Irrigation water management practices are the timing and regulation of irrigation water applications so that the water requirements of the crop are satisfied without wasting water or losing soil. Water is applied in amounts that can be held in the soil for crop needs and at rates that do not cause runoff and erosion. The irrigator provides the management, not the structure. For example, an irrigator may install a head gate to control the flow of water into the field. The head gate itself provides no water management. The water is managed when the irrigator opens the gate to deliver water to the field or closes the gate to stop delivery. Before irrigating, the irrigator must decide, for example, when to open the gate, how far it should be open, and when it should be closed. The ability to make sound water management decisions is the most important aspect of conservation irrigation water management. To make sound decisions, the irrigator must understand the basic principles involved. He or she must have a general idea of how water is held in the soil for plant use and how much water the soil holds. The irrigator needs to know how to judge when irrigation is needed and how much is needed. He or she should have a general understanding of soil intake characteristics and of the required adjustments in stream sizes and time of water application according to the intake rates of the soils. Regarding irrigation water management, the main objectives of NRCS are to give farmers an understanding of conservation irrigation principles, show them how to judge the effectiveness of their own irrigation practices, and help them make needed adjustments in old systems or install new systems.